G'day guys, Mr. Bennett here. Now today we're going to be looking at exercise 4D3, which goes through finding all possible answers to a curve where x is equal to pi on 6 for between 0 and 6 pi. Okay, so if we were going to do that, then what I would be considering for this first one, and it relates to what we did in our last video. So for here, what we've got to do is simply look at the value of pi on 6, and we're going to add that. So we can have values of k is equal to 0, 1, 2. Now, I think the easiest way to do this is to consider the following. All right, so if we're going to do this, when I'm thinking my k value is going to be 0, 1, 2, 3. I want to consider that value there as, now I want to put it the same as what pi on 6 is, and that's going to be 12 pi on 6. And there I need to consider that value as being in pi's on 6, so that's going to be 36 pi on 6. And that will make life a little bit easier for me in terms of thinking about this. So if k is equal to 0, then x is going to be equal to pi on 6. If k is equal to 1, then I'm going to add one lot of 12 pi on 6, so therefore that will become 13 pi on 6. 1 plus 12. I'm just going to go up in multiples of 12 pi on 6. The next one's going to be plus another 12, so that's going to be 25 pi on 6. And then I'm going to add another 12, which will give me to 37 pi on 6. Now, the problem with this one here is that's greater than 36 pi on 6, so therefore I'm not going to consider that value. I'm only going to consider those three values there. That makes sense. Let's do one more for there, just to get you the idea. Alright, pi's on 3. I'm going to consider that being 6 pi on 3. Right, from negative 2 pi, it's going to be negative 6 pi on 3. And that's going to be 6 pi on 3. Looking at my regions. Now obviously k can be equal to 0, 1, 2, 3. It could be any multiples. So if I'm thinking of x being equal to negative pi on 3, I'm going to add, or k could be equal to negative value, couldn't it? If I'm going to think about a value, if I'm taking that, if I take a value of that, so that's going to give me negative, and that becomes negative 7 pi on 3, because that's what I'm doing, multiples of 6 pi on 3. That's not going to fit in there, so that's not going to consider. If I'm adding that now, I'm going to go negative pi on 3 plus 6 pi on 3 is going to give me 5 pi on 3. And that's actually inside our region, so that one's not going to be considered. And these other values are. So the two values I've got for there are going to be negative pi on 3 and 5 pi on 3 are the only values. Alright, this is the next bit, and this is the tricky bit that I find students do find this difficult. But we'll just go through this and hopefully it'll make sense to you. So question 2, I'm going to work through this, and I'm going to do this algebraically for you. 2a. If I get given something like 2 sine x equals 1/2, and we know that our x goes between 0 and 6 pi. Okay, so therefore, I've already done the rearrangement. What a goose. I've got that as 1. Alright, so then what we can say here is sine of x is equal to 1/2, isn't it? And that's, so if we're thinking about our unit circle, where's sine positive? Sine's positive here, and sine's positive there. Dropping our right angles down here, that's 1 and that's 1. 2, 2. Here we know that this angle here, or this side over here, is root 3. that is negative root 3. So therefore, this is actually pi on 6. And that's going to be pi on 6 over there, isn't it? So therefore, the two angles that we're going to have for our circle rotation is sine of x. X is going to be equal to pi on 6. And so that's the first angle, is pi on 6. The second angle we're going to have is pi on 6 short of pi. So it's going to be simply that, or 5 pi on 6. And then we're going to add multiples of k to pi. So just to make life a little bit easier for us, just put these values in terms of the values of pi on 6. So over here we have 6 pi on 6, which is going to be 36 pi on 6, isn't it? K 2 pi is going to be 12 pi on 6. Got the idea? So therefore, the values that we can have for x are the following. The values that we can have are x is equal to pi on 6 or 5 pi on 6. That's when our k value is equal to 0. Right? So that's our two values there when k is equal to 0. The next value we can have is add a 12 pi on 6. So that's going to be 13 pi on 6. 5 plus 12 is going to be 17 pi on 6. That happens when our k value is equal to 1. Right? And we're going to keep going until we get to 36 pi on 6. 13 plus 12 is going to give me 25 pi on 6. And then that's going to give me 17 plus 12 is going to be 29 pi on 6. And that's going to be when our k value is, in fact, equal to 2. And then we could keep going again. If we go 25 plus 12 is going to be 37 pi on 6. And then we've got 29 plus, that's going to be 41 pi on 6. Now, they would occur when k is equal to 3. But because the greater than the value over here, which is our upper value, 36 pi on 6, what we have to do is not count these. We can't count those. So there would be 4 points of contact for that curve between 0 and 6 pi. Now, I want to show you algebraic or graphically what that looks like. Okay, so we're looking at sine of x equal to 0.5. Clear that. So 0.5 or 1 divided by 2. And we know that we go from our value here, our x value goes between 0 and 6 pi. So 6 pi is that graph there. So if we graph that, so this is what our sine of x looks like between 0 and 6 pi. So this one here is, this point here would be pi on 6, 5 pi on 6, 13 pi on 6, that would be 17 pi on 6, that would be 25 pi on 6, that would be 29 pi on 6, corresponding to those points that we have on our curve over here. Alright, so I'll leave the video here for now. I'm going to do another one of these, and I'll actually do another 2 of these types of questions for you. But essentially, the graph's got to match with what we're expecting to see algebraically.